All right, welcome to Hovercraft Physics and Chemistry. This is a video on polyatomic ion hacks. So you may be in a chemistry class where you are required to know the charge and formula of various polyatomic ions, and if you are kind of a visual thinker, this setup might help you. You can actually build out a pretty good table, thorough table of polyatomic ions with this. And as a bonus, you will get some acids, names, and formulas as well. So really there's like 4 parts to this, and what I've done here is I've set up a paper with 8 blocks, so I've kind of folded it up. My notes are going to go here in the upper right corner, and these other boxes are going to represent different elements on the periodic table. So a lot of your polyatomic ions are based off of carbon, nitrogen, phosphorus, sulfur, chlorine, and then down the halogen row you see some trends there as well. So if you imagine my 8 blocks here on my big sheet of paper, I'm kind of right here, carbon, nitrogen. I'm not going to do oxygen or fluorine because most of these are oxyanions which contain oxygen. And fluorine does not have many stable polyatomic ions because it is so small and so electronegative. It doesn't form stable structures that we'll see with some of the other neighboring elements. So I'm going to go ahead and transfer some information to each block. So up here on the left, we're going to start with carbon. One block over, we have nitrogen. I've just listed the atomic number as well. Below carbon is silicon or silicon. Below nitrogen is phosphorus. Next to phosphorus is sulfur, atomic number 16. And then we have chlorine. Next to sulfur. Alright, so my first tip is to start with what I call the ATE anchors. These are very, very common polyatomic ions, and if you can remember the charge and formula of these 4, you can build out the rest of the table based on these. So my first ATE anchor is carbonate. Which has a formula of CO3 with a 2- or -2 charge. Next door is nitrate. Also NO3, but nitrate has a -1 charge. Below nitrate, there's going to be a trend that we'll see, a similar trend that we'll see in phosphate, sulfate. So phosphate is PO4 with a -3 charge. And then sulfate is SO4. And just like our charge went down 1 from 2 to 1, it does a similar decrease here from phosphate to sulfate. Sulfate's charge is -2. Okay. Now you won't see it in many introductory chemistry textbooks, but there is, if we go with that same trend to the left, there is a structure called silicate, or silicate. Silicate is how it's normally said. And following the trend here, it should be SiO4, and we go from -2 to -3, and it does have a -4 charge on it. So I'm not going to build out this box because you don't see it typically in introductory chemistry, but silicates are important in geology, in minerals. Now, I'm not going to write the name, but if I follow the trend through to chlorine, it would suggest that there is a polyatomic ion with the formula ClO4 going from 4, 3, 2, 1. And there is, but it's not called chlorate. This is one of these things that is annoying that chemists have done. It doesn't follow the trend. So I'm going to come back to that one. This does exist. It's a stable polyatomic ion, but it is named perchlorate. Back to that in a minute. So due to the importance of our ATE anchors, I'm going to highlight those in blue. Again, if you know those four, you can build a lot just used on patterns from there. So my next part of the hack is to do the Ite Partners. And to do an Ite partner, you always have one less oxygen but the same charge. Okay. Some of these are more common than others, and my understanding is that some polyatomic ions, although it's possible that they exist, are not very stable. They're very reactive, and they'll quickly react with something else. But some are super common, and you're going to run into those quite a bit. So one of the more common ones using the Ite partner rule is nitrite. And I'm going to kind of put that halfway down here. So nitrite should have one less oxygen, but the same charge. Okay. Sulfite is a pretty common one. I'll do that next. Sulfite will have one less oxygen, but the same charge. Now, carbonate and phosphite do exist, not super common. I'm going to go ahead for completeness to include those. In my reading, there is potentially something called silicate, but again, I'm going to kind of leave the silicon one for another time. We're not going to worry about those too much. But I will go ahead and do phosphite and carbonate. Decrease it to PO3, same charge. Carbonate, CO2, 2- charge. Quick refocus there. All right, going to leave chlorine and perchlorate for the end here too. So next hack is to add what I'll call the hydrogen partners. And when you add a hydrogen partner, you can think of adding an H+ ion to the polyatomic ion unit. So let's start with carbonate. If I add an H+ to carbonate, the formula will change to HCO3, and if it brings along a positive charge, that's going to change the charge of the polyatomic ion to -1. Okay? Now the standard name for that is hydrogen carbonate. It often goes by bicarbonate, which is a historical name that is somewhat persistent, but I'm going to call it hydrogen carbonate. I can't add another hydrogen. If I did, I would end up with a neutral particle. I'll come back to that idea in a second. I can do the same for carbonate. I can have hydrogen carbonate. Not super common, but it does exist. Phosphate is going to require me to be able to add 2 hydrogen to it. Okay, so hydrogen phosphate is HPO4 2- charge. I can also add a second hydrogen that's called dihydrogen phosphate. That's H2PO4. And now the charge is just -1. Sulfate over here. It also has a hydrogen sulfate version. HSO4 with a minus charge. I can do similar things for hydrogen phosphite and dihydrogen phosphite for the sake of time. Not super common. I'm not going to worry about those. But I think I will do it for hydrogen sulfite. Okay, so now we're going to look at what if I did add another hydrogen. So one thing we know about acids is we think of acids as being a particle that in water dissociates into a hydrogen H+ ion and a negative anion. If I think about the opposite of that, if I keep sticking on hydrogens, what I might end up with is a neutral acid formula, and that's exactly what I want to look at next. So if I were to stick another H+ on hydrogen carbonate, that would be H2CO3, and now it's neutral. It's actually the formula of an acid. So back to our acid naming rules, when it is based on an ATE ending, it takes an IC ending as an acid. So next I'm going to say acids with IC endings for 8 and OUS endings for polyatomic ions ending in ite. So H2CO3 is built from carbonate. It's called carbonic acid. If I add another hydrogen here to the phosphate grouping, I've got H3PO4. That's a neutral formula. That's phosphoric acid. If I do the same thing with phosphite and get all the way down to H3PO3, that's based on an Ite ending. That's phosphorus acid. Not a super common one, but that is how you would name it. If I go back to sulfate and add another H plus to the formula, it's H2SO4. It's an Ate ion. That is sulfuric acid. Not as common, but H2SO3 is going to be sulfurous acid. Same thing here, not super common, but if I follow down the trend, I guess I could have just added it. H2CO2 is Carbonus acid. And that one actually goes by a more common name, Formic acid. So if you've heard of Formic, that's kind of the historical name for Carbonus acid. Let's go to nitrate and nitrite. I didn't try to add an H plus to it. I didn't try to make a hydrogen partner because that alone would have made an acid. But if I add an H plus to nitrate, I've got HNO3 neutral formula. It's an ATE ending, so that is nitric acid. That is a super common acid. That's one you should probably know. HNO2, nitrous acid, not as common. The last step to kind of building out our list of polyatomic ions would be the chlorine naming. So again, I thought it would be nice if ClO4 with a minus charge was called chlorate. It is not. It is perchlorate. And we can add, or decrease the number of oxygen to come up with other polyatomic ions, always still having a minus charge. So we're kind of going back to this ITE, but it's a different naming scheme. So ClO3 with a minus charge, that is actually chlorate. I can drop it down one to ClO2 with a minus charge. That's chlorite. And if I go even one step further, ClO minus, that is hypochlorite. And then the last thing I might do is figure out what these would be named as acids. I haven't given myself a lot of room, but if I add an H to this, HClO4, it has an ATE ending. That is perchloric acid. I'll just put A, period. Chlorate HClO3 as an acid is chloric acid. Chlorite as an acid, HClO2- is just going to be called Chlorus acid. And then hypochlorite as an acid, sometimes written HOCl. It turns out that the hydrogen is actually bound to the oxygen in the molecule, is hypochlorous acid. And then one final thing, there are some extensions. If I go to the left of carbon on the periodic table, I have boron. And there is a borate ion. It does follow the trend, so it's going to be BO3 with 1, 2, -3 charge. And you can build polyatomic ions in a similar way. So there's a lot here. I'm just going to go through and highlight the most common ones that you would need to know beyond the anchors. I would say your oddly named chlorine oxyanions are important. The acids are not super common, but they're good to know as well. Hydrogen carbonate, good one to know. Carbonate, not so familiar, not so common. Nitrite for sure. A lot of common ion lists will list your hydrogen partners to phosphate. Phosphite, not so common. This one will be in a lot of common lists. Sulfite will be in a lot of common lists. And possibly hydrogen sulfite. So if you're the type of person that doesn't like to just memorize things, you might try to practice building out this chart. We've got a ton of common polyatomic ions here, some not so common polyatomic ions, and then also some common acids that would be good to know as well. Let me highlight those in pink. Your most common acids that you're going to come across in introductory chemistry would be nitric, sulfuric, I would say perchloric is pretty common. I'll go ahead and highlight the rest. Not as common. And then rounding out our other not super common acids, sulfurous, nitrous, carbonic, Carbonus, and so I've got a long list. Again, I would argue that if I can remember these 5 things and my anchors, I can work through and build out a pretty complete list of polyatomic ions and acids. I hope that helps. If you have any questions or if you notice a mistake I made, feel free to put it in the comments. Thank you.